So, we've always thought our universe runs on a pretty solid set of rules, right? A kind of grand cosmic instruction manual. But what if that manual has a typo? A huge, fundamental error that changes, well, everything. It's a discovery that's forcing scientists to ask a really uncomfortable question. And that's not just some clickbait title. It's the exact question cosmologists are asking themselves right now. A whole new flood of data has just come in, and you know what? It's suggesting that a core piece of our understanding of the cosmos might be completely, totally wrong. It all starts with this number, negative 0.156 electron volts. Now, that's just a tiny unit of energy, but when scientists plug the new data into their trusted standard model, this is the mass it spit out for a neutrino. And there's one teensy problem with that. Mass can't be negative. It's physically impossible. It's like finding a square circle. It is a mathematical scream telling us our theory is broken. Okay, let's dive in. We're going to start by looking at this crack that has just appeared in the very foundation of modern cosmology and unpack the data that's causing all this trouble. So this instruction manual we've been using for decades, it's called the Lambda-CDM model. And look, it's been incredibly successful. But it's all built on one giant assumption, that the mysterious force pushing the universe apart, what we call dark energy, is a constant. It's like a cosmic cruise control that was set to one speed and has never, ever changed. And this is where the fight starts. Our trusted theory, the standard model, demands constant dark energy, and, of course, that particles have a positive mass. But the brand new data from the DESI survey is pointing in the complete opposite direction. It suggests dark energy is not constant. And the moment you plug that evolving dark energy into the old model, you get that impossible, nonsensical negative mass. Now, to really get why this is such a big deal, we gotta talk about sigma. In physics, sigma is basically a confidence score. A 3 sigma result is considered pretty solid evidence, and a 5 sigma result is a full-blown discovery. So when the data comes back between 3.1 and 4.2 sigma, well, that's not just some little blip on a screen. That is a loud, persistent signal that something is fundamentally different than we thought. So if our old model is cracking at the seams, it's all because of this weird new behavior from dark energy. Let's take a closer look at what evolving really means for the entire recipe of our universe. And this right here shows you the problem perfectly. That line represents the strength of dark energy over billions of years. In the old model, that line should be perfectly flat, locked in place. But look at what the real data is showing us. It's not flat at all. It's curving. The universe's expansion isn't on cruise control. It feels like someone's foot is on the gas pedal, and it's changing. Yeah, a really good way to think about it is like this. The standard model assumed dark energy was just a simple on switch that got flipped at the beginning of time. This new data suggests it's much more like a dynamic throttle, with the power level actually changing as the universe gets older. So if the old theory is broken, what could possibly replace it? Well, a new suspect has just entered the room, and it's a really compelling idea called dynamic vacuum field theory, or DVFT for short. And it all starts with this pretty radical question. For decades, we've been hunting for dark energy like it's some exotic, mysterious fluid filling all of space. But what if we've been looking for the wrong thing this entire time? DVFT proposes something pretty profound. It says dark energy isn't an ingredient in the universe. It's a property of the universe itself. It suggests the vacuum of space isn't actually empty, but it's this dynamic field whose properties can literally change over time. And that's what produces the effects we call dark energy. The anti-gravity isn't in space, it is space. And look, this isn't just some wild guess somebody pulled out of thin air. DVFT is a serious, rigorous theory. It starts from fundamental principles, it applies its own unique math, and most importantly, it makes specific, testable predictions about the universe we should be able to see and measure. So, the big question, does it actually work? This is the moment of truth. Let's see how the predictions made by this new dynamic vacuum field theory actually stack up against all that strange new data that's breaking the old model. Okay, let's open up the evidence file. First up, the strength of dark energy today. The new DESI data puts it around negative 0.78. DVFT predicts it should be between negative 0.8 and negative 0.9. That is an incredible match. Then there's the question of how dark energy is evolving. DVFT makes a prediction for that too. But the really stunning part? The neutrino mass. right where the standard model completely falls apart. DVFT naturally predicts a small positive mass that fits the data perfectly. And this, right here, this is the smoking gun. That central, universe-breaking problem of a negative particle mass, in DVFT, it just vanishes. It's not a patch, it's not a fix. The theory, from its very core, just naturally predicts a small, positive mass for neutrinos, perfectly lining up with reality. Problem solved. But wait, there's more. It turns out DFT also helps with a bunch of other cosmic headaches. It predicts a value for the universe's expansion rate, the Hubble constant, that helps solve a major debate in cosmology. It also matches new hints about how galaxies and clusters grow over time. And, maybe the most mind-blowing thing of all, it might even explain the effects of dark matter without needing some mysterious new particle to do it. So what happens now? I mean, while DVFT is looking like a really compelling suspect, this cosmic case is not closed yet. Not by a long shot. The investigation is just getting started, and a lot more evidence is on the way. So here's what you need to be watching for. This year, 2025, gave us those first big, tantalizing clues from the DESI and Euclid telescopes. But the really big one is coming in 2026. That's when we get the first major data release from the Euclid mission, and it's going to give us the sharpest view of dark energy we have ever had. It could be the evidence that finally confirms this whole new picture of the cosmos, or sends everyone back to the drawing board. And that just leaves us with this one final thought. We have spent an entire century searching the heavens for exotic particles and mysterious forces to explain the universe. But just maybe, the answer wasn't out there at all. Maybe it's been right here, all along, hidden in the very fabric of nothingness itself.